Hello everyone, welcome to today's webinar. Before we get started, I'd like to go over a few items. Here we have a screenshot of the attendee interface. You should see something that looks like this on your own computer desktop. By default, you're listening in using your computer's speaker system. If you would prefer to join over the phone, select Phone Call in the Audio tab and the dial-in information will be displayed. For those of you viewing live, you will have the opportunity to submit questions via the Questions tab in the control panel. You may send your questions at any time during the presentation, and we will address them in the Q&A session at the end. You might also find some helpful resources in the Handout tab of the control panel. After today's presentation, we will have a recording available, so no need to take notes, just focus on the presentation. Keep an eye out for an email from us with the recording. During the webinar, we will share a QR code with a short survey so you can provide feedback and identify how we can best serve you. And of course, stay tuned for our next webinar. Let's get started. Virtuosity is Bentley's e-store, which offers 12-month practitioner licenses of Bentley software paired with customizable training and support. We call this a Virtuoso subscription. Virtuoso subscriptions include your 12-month software license plus keys that can be redeemed to unlock customizable training, mentoring, and consulting services. The number of keys received with each Virtuoso subscription varies based on the software you choose and replenishes every 12 months. Continually enhance your skills with new software, workflows, systems, and other innovative technology. Shop now at virtuosity.com.
Hello, Cal. Your mic is muted.
Hello everyone. Good morning, good afternoon, and good evening. Thank you for joining today's webinar. So today's topic is stability analysis of a mechanically stabilized Earth MSE wall with slope W. So let me introduce our speakers today. So Fazin Hamadi will be our technical speaker. So he's our geotechnical engineer from Sequent Bentley, and also myself, Kyle Shen, sales engineer for GeoStudio products in ANZ from Bentley Sequent. So here is our agenda. So first of all, I'll introduce Bentley Geotechnical Engineering Solution and hand over to the Fazin for the demonstration of GeoStudio, and back to me for Virtuosity Practitioner License introduction, and back to Fazin again for Q&A and finish. So first of all, let's see what Bentley Geotechnical Engineering Solutions is. Let's say what is Bentley and Sequent. Bentley provides all different kind of software for building construction, engineering analysis, environmental infrastructure and mining, and so on. About 3 years ago, 2.5 years ago, Sequent joined Bentley. So with its legacy products, Leapfrog, GeoStudio, Oasis Montage, and so on, together with Bentley Geotech products, Pluxys, gained open ground. So all those products form the subsurface world of Bentley. So all those subsurface parts are taken care by the Sequent. So here are the Bentley Geotechnical Engineering portfolio. What we focus on today is GeoStudio. It is a tool for the geotech analysis. And we also have Pluxys 2D, 3D, and Multiply Designer. So Pluxys and GeoStudio forms the geotech analysis portfolio. In the other side, we have GINT, Kinetics, and Open Ground for the geotechnical information data management tool. If you have any question about other products, let me know. So let's focus on GeoStudio. GeoStudio is a tool for geotechnical and geoenvironmental analysis and design. There are several products and tiers underneath. GeoStudio 2D, 3D, 2D, 3D Advanced, and 2D, 3D Ultimate, and the GeoStudio Flow. GeoStudio 2D offers a foundational capability to perform limit equilibrium slope stability analysis for soil and rock. GeoStudio 2D Advanced offers all the essential capabilities of the GeoStudio 2D tier while introducing the ability to simulate steady state and transit groundwater flow in both saturated and unsaturated soil and rock. GeoStudio 2D Ultimate expands the capability of the GeoStudio 2D Advanced tier with functionality to deal with the most challenging geotechnical projects. Includes features to analyze static and dynamic stress and deformation within soil and rock, coupled consolidation, and final element stability methods. GeoStudio Flow offers a range of numerical analysis tools for simulating geoenvironmental conditions above and below the ground surface. GeoStudio Flow can be used for a range of applications, including excavation and open pit mines, dewatering system, earthen dams and levees, tailing storage facility, and waste cover system. Okay. So before the demonstration, we have few poll questions. Let me launch the poll question and please answer those poll questions. The first one. Have you ever used GeoStudio before? Please click the button to vote yes or no. Okay. Let's wait for 20 more seconds to close this vote. Okay, 10 more seconds. Okay, close it. And here is a second poll question. What do you usually use the GeoStudio for? Slope stability, dams, levees, and embankments, excavation, others, or I'm new to GeoStudio? Okay, 20 more seconds. Yes, 10 more seconds. Seems more people want to vote. Okay, let's end. And thank you so much for the voting those poll questions. The next one we're gonna have is a demonstration from Fading. And yeah, just reminds everyone, if you have any question, no matter it's technical question about GeoStudio, about this question about this demonstration or about the virtuosity, please feel free to input your question in the box. And during the Q&A session, Fazin or me or anyone, yeah, any of us could answer the questions. Yep. Okay, I'm gonna bring in the Fazin to demonstrate.
Welcome in today's webinar. My name is Farzin Hamidi. I'm a geotech engineer based in Brisbane, in Australia. In today's webinar, I'm going to cover how to analyze stability of an MSE wall with a slope W. In today's webinar, we'll briefly review the theory and background behind this topic, and we're going to cover a case study of a large MSE wall. First, we review the project geometry. Then, in a short demo, we are going to cover the difference between the global stability and internal stability and see the effect of reinforcements on convergence. Let's get started with the theory and background behind this topic. When you add reinforcements to any geotechnical system, like a retaining wall or a slope, it becomes a soil structure interaction problem. Consider the anchor supported excavation shown here. The anchor has a free length and a bounded length. The load that is transferred into the anchor depends on the ground movement or a pre-tensioning post-installation. Pre-tensioning the anchor causes shearing at the interface between the bounded length and the ground. Similarly, the active earth pressure acting on the wall lead to the deformation, causing the elongation of the anchor. The bounded lengths transfer the applied tensile load into the ground. In a limit equilibrium analysis, the effect of reinforcements is represented using a point load. All reinforcements is fundamentally the same. It is assumed soil structure interaction transfer load through the reinforcements and into the ground profile. We must therefore convert the shear mobilized behind the slip surface into the pull-out force acting on a sliding mass. The pull-out force or reinforcements load depends on the number of factors including the pull-out resistance, which characterize the shear resistance mobilized at the interface between the reinforcements, the area of a reinforcement behind the slip surface depends on the length of a reinforcements behind that slip surface, the tensile capacity of the reinforcements, a reduction factor to account for lifespan, temperature, or pH, and more. And finally, the presence of anchorage at the face of reinforcements, at the face of the wall, let's say it this way. In a slope W, there are other considerations for defining a geosynthetic. First, the pull-out resistance calculation. Geosynthetic derive their shear mobilized via frictional resistance at the interface. As such, the pull-out resistance increases with the depth of fabric at the effective overburden stress increases. To model this scenario, we must choose the option shown on the screen. Enter the interface adhesion, friction angle, surface area factor, and the reduction factor. The surface area factor is generally set to 2 to account for shear mobilized on both sides of the fabric. The second point in here is the anchorage at the face. Geosynthetic and geogrid are often anchored at the ground surface, either directly or indirectly by wrapping the fabric up to the face and back into the ground profile. The presence of the face anchorage ensures that the reinforcements behind the sliding mass can mobilize resistance. However, if face anchorage is not present, then it is possible that the soil could strip off. Slope W calculate the pull-out force mobilized behind the slip surface and within the slip surface and select the smaller of the two, and the smaller of these two values are considered as a pull-out load, which cannot exceed the reinforcement's tensile capacity. We're going to cover quickly about external and internal stability here. It is important to differentiate between internal and external stability. Most mechanical stabilized walls include wall facing, geogrid, backfill, and the naturally retained material behind the MSE wall. The MSE wall can effectively be thought of as a single block. In this case, the mode of failure under consideration in a slope W is either circular by using the entry and exit for a slip surface option, or it could be base sliding using the block specified search. In contrast, internal mode of failure consider a bilinear failure that passes entirely through the MSE wall. Although slope W analyze could be used to check for mode of failure that sits within the MSE wall, the analyze will often suffer from convergence problem due to the number of reinforcements point loads applied to the sliding mass. Convergence problem can arise due to three main reasons: high strength contrast between materials, sharp corner in the trial slip surfaces, and concentrated point load. Ultimately, the last two issues are the same as the first issue because sharp corner at the point loads often cause an increase effective base normal, which resulting in increase of strength on a particular slice. We can solve this problem by reducing the strength contrast. In dealing with this point load, we need to distribute the load over many slices versus just a single slices which actually applied. Let's talk about the case study. An MSE wall was constructed to accommodate roadway along a perimeter of a steep slope using a McCaffrey Tromesh rock wall system. The Tromesh system consists of a pre-assembled wire mesh units used to confine stones. The unit is constructed using a continuous panel of mesh that comprise a base, faces, lead, and a diaphragm, which is considered as a dividing walls. The length of the base behind the gabion is a project specified, and that's why it's varied in this picture. The stratigraphy comprise a foundation soil, backfill material, and a structural soil which is used as a backfill behind gabions. The MSE wall was constructed in 4 benches with batter walls having a face inclination of 5.7 degrees from vertical. Construction commenced with the placement of gabion system. Each gabion had a height and a width of 1 and 2 meters respectively. The steel wire mesh extend to the behind of the face of the wall. A structural soil was placed behind the wall up to the grade with the top of gabion. A McCaffrey 300 geogrid, which shown in blue, was then installed prior to the construction of the next layer. The length of each paralink geogrid was governed by the distance from the wall to the face of the hill slopes. Let's now turn into GeoStudio and review the setup of this analysis.
This is the final problem that we want to build in GeoStudio. I'm going to quickly go through the steps of creating this model. I'll try to cover the majority of us constructing this model in this webinars. But if you need any further clarification, I will refer you to the PDF file. Let's get started with the geometry first. As you can see here, the geometry is created in a CAD and then I import it into GeoStudio. So first the foundation soil. As you can see, it's a backfill soil, it's a structural soil, and gabion block. and also the region, as you can see here, is all available in these CAD. So you have to make sure your CAD's polylines are closed, then you will be able to import it into GeoStudio. Also, those polylines should not have any overlap to each other. So these are the two things you need to consider when you create your CAD file. This is the model that I created for a build-up, the same model that we have available online. So you can actually download this model and see it online, available with a PDF guide. But I'm going to step by step creating this model. First, you need to import that geometry which we earlier show you in a CAD file. Simply you click on the file and then move into the import. Once you are in import, you can see the geometry is created here. Just insert that geometry. You will see this menu appears on your screen. As you can see, everything is as by default is selected, so we'll leave as is selected, but I just want to highlight some points. When you click and apply, you can still have a change and it's still connected to the file. So once you click, you see the only thing is imported is geometry because I didn't toggle this on. So you can actually toggle this on to import all of them, or you can actually select from the menu. I don't need the, for example, the region is imported because it's going to be an overlap. I mainly imported the material name that I need to then assign the material property for them. Once I select them, once I toggle this on, then I click apply, you will see the color, the same coloring is appear here. So you can actually bring them all into GeoStudio and run your simulation. And there's also another toggle here. As you can see, it's currently this X axis is aligned with the vertical axis. So you can actually see my X axis is exactly aligned with the vertical axis, because I actually said that translate the horizontal to 0. If I translate the vertical to 0, you'll see the red axis is also here, and this is going to be 0 point for my material. But I just want to skip that and I just leave it into horizontal 0. The other thing that you can do is just simplify your model. I just want to highlight this, but I'm not going to do that. You can actually simplify the point segments into your model to actually reduce the file and also the constraints later on in your mesh generation if you wish to do the finite element modeling. So you can actually click on this and simplify the model. As you can see, the line segments is reduced substantially when you remove them, and you might lose some of the complexity in your model. And from a specific point, your model looks a bit weird. So just leave it as it was, and you can see exactly how it looks like. That's it. That was available in my model. I'm going to import it. I'm happy with it, and then I click OK. With that done, as you can see, I already created a project tree with the geometry, the 2D geometry. You can actually adjust it later here. You can actually change the project name here, and also the geometry, the out of plan thickness. I just leave it as is. I'm going to add a slope W analysis here. You can simply see the slope W analysis, which was exactly identical to what I had. I'm going to rename it here, same name. So the geometry is almost appears on my screen, and I already put a dimension already here, so you can actually do the same thing, add the dimensions, and everything is available for you to run your analysis. So these are the things that you can consider to bring the geometry. You can actually zoom into the geometry, extend, and everything is appears here. And as you can see, this material is predefined. I have the material property already in this file. I don't want to allocate time in putting them in, but I just want to show you how you can actually see this material. So you see the unit weight, the effective cohesion, and the effective friction angle is already imported into this model. As you can see, here is the material table that I have available here. So you can actually bring the material table anywhere into your screen and add it here. You can adjust it. For example, you can add a specific particle or not. For example, 5 is not included in my model. I'm going to exclude it. I don't want to have the material naming, material name. That's it. That's how it works. You can actually change the style, size of the font, and everything here as well. Add it for all the analysis or specifically to this analysis. So I'm going to close this, Control Z. In the GeoStudio, you do have the option to do Control Z and Control Y for redo and undo. And then I just want to show you the material. Let's review the material property for this specific geometry. As you can see, all the materials are considered as mole coulomb. So the mole coulomb, you just need to simply put the unit weight, effective cohesion, and effective friction angle. So there are some suctions parameters which is not included. As you see, 5B was already shown there 0, and the rest of them in an advanced tab available. So you do have an option to put the legend here for your material, just the coloring. But yeah, since I already included, I just exclude it from here. I have to note here that first we are going to do analysis without reinforcements. So with this geometry that we created, so we don't consider any sort of reinforcements in here. Also, the Gaussian system considered as part of geometry. We don't include modeling the Taramesh properties in this model because that's only considered as a geometry item in my model. I'm going to go through the properties of reinforcements. So you have to go to the define again, and under the reinforcements, you will see also I already defined the McCaffrey paralink. I just want to review the parameters here. So you can actually see the McCaffrey paralink is part of GeoStudio library. So we do have library available for other providers such as Husker, McCaffrey, Tenkate, and Tensor. So as I explained during the presentation, so the Paralink 300 is selected from these models that you can see they are available here. You can select particle size distribution, basically based on the GeoGrid provider, and the field material can be changed, and it eventually these input parameters are going to be calculated and affecting the output parameters, and eventually you will see them in a pull-out resistance force because you do have a pull-out coefficient as well as the tensile capacity, which is calculated here. So everything that you have as an input is going to affecting your output results here. So we are going to include seismic analysis, temperature, design life, and a pH is going to affect our reduction factor. So that's why we don't include it here. We're going to, it's going to eventually calculate an overall reduction factor is going to be calculated here. We consider phase anchorage as true, as explained in your presentation, as well as the force distribution in order to consider the convergence. We're actually distributing the load instead of having a concentrated load applied. I'm going to close it and I will show you how we actually set up the reinforcements step by step. Once you're done with your properties and the reinforcements property, you can actually go and add another analysis, because the first analysis without reinforcements, you can do it here and simply go to the definition view and clone the analysis and rename the second analysis with reinforcements. So the reinforcements option available with the seismic load. So the first analysis, as it appears, is the Morgenstern price. And the method of analysis, all the rest of them are identical. So the slip surface definition, left to right, entry and exit. There's no tensile crack as well included. We are set to add your reinforcements. There's an option for you to add reinforcements individually or in a group. So I'm going to select it in a group, and basically based on the reinforcements option that I have, I can simply go and click the first point and the second point, which is the end of the first reinforcements, and you can see it shows in my screen how it looks like, the reinforcement. And I need to select the last point on the face of this wall. So I will select it somewhere randomly here, and I adjust it accordingly to the one that I want. So I can simply come back here and adjust the last point, let's say, to the point that I want. And you can add a specific length, actually absolute length, or you can actually consider it horizontally. So from the left, it actually changed the length of these reinforcements. As you can see, the left is changed. If I set it to right, it's going to change it into the right side. But yeah, that's the one I want. So you can actually see it action appears. So evenly distributed, or you can actually put a spacing here. At the moment, it's a spacing 8 reinforcements in that similar area, or 2 reinforcements in the similar area. I will select, let's say, vertically distributed, and also I just want to have a distance spacing between those reinforcements equal to 1. And then we are going to have 4 reinforcement set up in this model. So that this one doesn't need to be locked to the ground surface, because the first 2 reinforcements, it's not in the ground level. The ground level indicated in green. As you can see, these 2 are embedded into the foundation soil. Once I close, since I do not select the reinforcements material, you will see them not colored, and then I can switch back and change it later on. So see, it's grayed out. I can go back either in draw or define. I will go to the draw and get back to the reinforcement set. Anytime you can actually get back to reinforcement set and change, tweak it, and anything you can do here. Or you can actually ungroup them and individually change them. So I just want to rename it into the similar name that I have in my original file. So this is the first bench, and I'm going to assign it to the similar material that I already shown earlier. So this is the material, and it's going to show everything correctly in my screen. So you can actually do the same thing. You just simply select the second point. Similarly, so let's close this one, and then as you can see here, everything is set up. I'm going to skip through the rest of them, and I will open up the file with the completed version of the reinforcement set. Add some seismic load capability. So there are some fraction of your gravity. So they actually, you can add those forces horizontally or vertically to simulate a similar behavior of, let's say, earthquake shaking, and the effect of that earthquake shaking is going to be replicated by the force, which can be applied only horizontally or vertically as well. 0.062 and also 0.03 for vertical. You can actually draw the slip surface anytime and tweak it later on. So the entry and exit range for my model is going to be somewhere around here, and it's going to be ended up in the second bench somewhere around here. But I can adjust it according to the original document that I have here. I can copy and paste it here, and you can see it is adjusted accordingly. That's a quick tweak, and I can actually change the number of increments in each segment entry, and also segment exit range, as well as the radius of this. So it actually increased the number of slip surface that is going to be tried. Copy and paste this slip surface by just clicking on this icon here, replace in analysis, or you can actually find it here, replace in analysis, whatever you want to select. Under here, you can actually transfer your slip surface definition, or anything from here. It can be transferred from the single analysis to the another analysis. So for the third analysis, I already defined the slip surface. I just want to move it and actually copy it for the first and the second analysis, a similar slip surface definition. I'm going to apply and click OK, and when I go to them, I will see a similar slip surface definition. See, the reinforcements option is not available on the last analysis as well. I can simply go there and select the reinforcements and copy it in analysis 3 only. Just want to make everything identical to what I had. So that's the way. And as you can see, once I'm done, it says reinforcements, line successfully replaced. Once I go to this analysis, I will see the reinforcements in action in the number 2 and 3. So everything is identical to number 2 and 3 except the seismic load. Anything is identical to number 1 and 2 except the reinforcements. So you won't have the reinforcements in the number 1, you do have it in number 2. So that's the way you can actually set up your analysis to see and to compare your results. You can draw surcharge load on top of this slope, which resembling, let's say, a traffic load on top of this slope, or it could be a crane load. So you can actually select the distributed load, you put a density on it, and in a unit weight, you can add a value of a force. So you can actually draw, since I select this point, and 1 meter as a unity, whatever I select, I'll go 1 meter here, and then the last point could be somewhere around, since I don't want to snap into the grid, I will select somewhere around here-ish, and it's actually create a distributed load. I'll click down and I'll go to the define, and I can tweak it later on. In here, you see my line is segmented into different line segments. So that's it. You can see at the moment the distributed load is only assigned to the first analysis. Similar way, you can go here and surcharge load, apply to number 2 and 3, apply, that's it. So the similar surcharge load apply to the number 2 and 3. I'll switch to the one with the result, and I will go through, cover some result interpretation soon. Here is the completed file. As you can see here, we included the extra tree analysis into this project tree. The rest of the analysis also included here, including all the reinforcement set, which is more completed to the one that we developed together. We only developed the benches, the first benches, but in this analysis, you see all the reinforcement sets are set up correctly up to the top of the surfaces. And you see the seismic load is applied. The only difference between this one and the previous one, 3 with the seismic number 3 analysis number 3, is that with the global stability we changed the slip surface definition in a way to actually be considered a more global sort of failure. We can capture the global failure, but in here we just try to capture a more localized failure. Analysis number 5, we actually try to capture the slip surfaces which is passed through the toe of the second bench, sort of an internal stability instead of external one. So we just want to have a quick understanding of what's happening if we do the internal stability for bench 2 and bench 3, and the slip surface is going to pass through them. So for the first analysis without any reinforcements, when we switch to the result view, you will see the factor of safety is 0.5-ish. So you can see the effect of reinforcements in the next analysis, because the only difference between the first and the second analysis, and when you include the Paralink 300 in your analysis, you will see the substantial effect in the factor of safety. If you go through the draw and graph view, you see the factor of safety and also the factor of safety versus lambda, and it actually shows you it's not an ambiguous shape of failure. So most of them are properly converged because we actually distribute the load properly among the reinforcements. That seismic, which is going to be applied horizontally and vertically, is going to reduce a bit factor of safety, which, as you can expect, that the only difference between the analysis 2 and 3 is the seismic load, and you will see the effect of that seismic load onto your slip stability analysis. The other thing I'll have to highlight it here, with the new release of GeoStudio, you do have an option to see the reinforcements load. Saw it earlier when we want to actually do the analysis, view object information, you will be able to see exactly what is the reinforcements load here, and it's shown with the new GeoStudio version, with the new release, which is 2024.1. you can actually see the reinforcement flow. The other thing you can see in the new version is the table that is provided the result view. So we didn't have this reinforcement line before. With the new version, you can actually include the result view for all your reinforcements or for a specific one. Since we have a lot of GeoGrid PowerLink, so you can see this result view is going to be big. So you can actually exclude them specifically or only include some of them, but you can add extra information to this one. For example, you will see at the moment in this view, you have the ID, you have the force, pull-out force that is applied, and you can actually have the available lengths behind this. For example, whatever was available in a result information for that specific anchor, you can actually put it in a table and view it for your report. The pull-out resistance for geosynthetic is calculated basically based on the overburden pressure in this example. When you click on this one, this dotted line shows that this specific geosynthetic is actually failed due to the tensile capacity. So the tensile capacity was the threshold in this specific one. The pull-out resistance are more than the tensile capacity. So the 275-ish is considered as the pull-out resistance, which is the marginal takes, let's say the maximum that it can reach, which is the tensile capacity. But for this one specifically, which actually failed with the pull-out resistance, it is specifically mentioned the governing component was pull-out resistance, and the force is shown here. You can see them all here as well as this one. Also, there you can see the available lengths in a color red box here. So this available length is exactly identical to what we have here, as well as you can see it in that table that I earlier showed you. There is also try in this specific project tree to check the internal stability. As you can see in the third bench, when I check it with the global stability 1.5-ish and with the localized one, which was 1.3-ish, this internal stability is actually behave differently. This is also 2.2, which is for the only two top benches. The interesting point is that typically, although we allocated the slip surface to pass through the MSE wall, but the slope that we try to actually avoid that and go through due to the extra resistance that we have to include all the capacity from those MSE wall. We have 4,096 slip surfaces. So out of that, with the second analysis, we have almost, let's go only for a valid slip surfaces. It's 2,600 out of 4,000, let's say roughly 3,000 in the first analysis. When we incorporate reinforcements, so the reinforcements, as we mentioned earlier, it might trigger some convergence issue. So some of them are not properly converged. So you have to check these in slip surfaces specifically, which is not going to be a critical one that we miss. So you have to go through them. As you can see, the reinforcements with the global stability has much more valid slip surface. But when we get into the internal stability, the number of valid slip surface says which could converge properly is substantially reduced. Okay, I will stop here and I will move on to the conclusion slide to provide you some online resources, and we will end up these webinars after that. I'm going to conclude today's webinar with a conclusion by just introducing some online resources available on our website. You can find some online courses, which could be Slope W Fundamental, SIP W Fundamental, GeoStudio 3D Fundamental, and GeoStudio Basic, which is all simply the GeoStudio interface. If you want to make yourself familiar with these physics as well as the GeoStudio interface, feel free to go and watch these courses online, which is for free, and you just need to create your Sequent ID and get access to these online learning resources. There's also product manuals available for engineering books if you need to have an understanding of the theory behind the solver, feel free to watch out our engineering books and find them under the resources, as you can see here. Also, there are some example files as you can see under the resources. There are engineering support available on mysequent.com. If you want to send us a support ticket, feel free to lodge a support ticket on mysequent.com, as well as the previous webinars are available to watch on demand. Feel free to watch our previous webinar. If you have any question, we're more than happy to hear from you. Thanks for listening to this webinar today. We look forward to hear from you. Have a great rest of your day.
Okay, thank you for Ding. That was an excellent demonstration. Yeah. So, and I'll just mention again that just remind you guys, if you have question, you're welcome to raise your question, and later on in the Q&A, Fazin will give the answer. So let's move on. A few other exciting things to show. Yeah. There is another poll question for you guys. Let me launch it. Okay, would you like a product engineer to contact you? Please click the button to vote yes or no. Let's keep it for 20 more seconds before we close it. Okay, almost here. Thank you. Okay, let's continue. Yeah, now let me introduce a bit about the Virtuosity Practitioner license. So here you can see this is a web page of our Virtuosity eStore. So you can like browse our website eStore to find out some software interesting to know its function features. And you can go ahead for purchase and the purchase of software and the servers. You can also search for some like training, webinars, recorded videos, some other learning materials. Yeah, you're welcome to go there, browse and search something you're looking for. So who can purchase Virtuosity subscription? So just be simple, anyone can purchase and use our license and the service. So that includes solo practitioner or part of a big organization projects, no matter you are existing Bentley users or non-Bentley users. So how long does it last? 12 months. So what Virtuosity subscription includes? So most importantly, it includes a practitioner license of GeoStudio. It is named user license, cannot be shared simultaneously or non-simultaneously, but the user can be switched to another different user every 30 days. It's a yearly investment, 12-month subscription, and it's one-off. There's no additional maintenance or service fee to pay. So you fully control your software costs. And during the subscription, you have our technical support to help you. And during the 12-month subscription, if any new version released, you're able to free upgrade your software. So once you click the Virtuosity Geotechnical Engineering sequence, you can see those geotechnical products. Like on the top, you can see GeoStudio 2D, 3D, Flow, and again, you roll down to mid or bottom, you can see other products, Fluxys or Open Ground. Now let's move to Fazin for Q&A parts. Fazin, I will give you as presenter. Yep.
Hey, Carl. And thanks everyone for joining us today. And yeah, just feel free to put your question in the chat box. And thanks, Carl, for the nice presentation. If you have any question, feel free to put it in the chat box, or feel free to send us an email. We are always available for helping you. I'm going through some of the questions that I already answered during the live session, privately to the people during the live session. So the first question was the result displacement. So is it possible to show the result displacement? So it is worth to note that the limit equilibrium analysis, you cannot handle the displacement within the limit equilibrium analysis, because the base of the method is basically based on the static equilibrium. So you actually use the force equilibrium method to run your analysis. So those forces are only activated in each specific, it's only valid for each specific trial slip surfaces. So you cannot actually have an interpretation of the displacement. Let me just go to the next questions from the audience. If you have any follow-up to this question, please feel free to put it in the chat. I will get back to you soon. One of you asking why some of the reinforcements having zero load. That's a good question, because those specific reinforcements has not engaged because the slip surface passed behind them. So if the slip surface passing the entire length of let's say reinforcements or those paralink geogrids, so it won't actually engage them in that specific slip surface. But if you go through the different slip surfaces, you can see different engagement, and also you can see the load. Specifically, you can see in that screen which specific let's say geogrid is engaged. I'm going to show my screen. Share my screen. Bear with me a sec. If I can figure it out how to share. All right. Bear with me a sec. I will share my screen. You can see now my screen, which is the Windows. I'm going to quickly go to the same example. So that's a question he asked, why these are shown as zero, because they're not engaged, and the slip surfaces that we have here is actually passed behind that. For example, I'm currently in a critical slip surface, which is highlighted in white. I'm going to actually reduce the complexity here and only including the slip surfaces which is included here. So as you can see, this slip surfaces passed behind this one. So this reinforcements is not engaged, but this one is specifically engaged, and you will see the load associated to that one. And some of you asked, some of these geogrids are failed with a tensile capacity. So the failing doesn't mean that the geogrid is not, let's say, so it fails and it's not activated anymore. The maximum capacity of that geogrid is going to apply to these slip surfaces, because as I mentioned, the limit equilibrium analysis is mainly talking about the force equilibrium. So in that specific geogrid, which we have 275.54, so it means that we engage the
the entire capacity of this GeoGrid in that specific slip surface. But if I switch to the different slip surface, you will see different behavior for each of them, and you can see exactly which. So the highlighted white one is the different one, but I can switch to the different trial slip surfaces that I earlier show you and see exactly which reinforcement is engaged and what is the load which is included in my, let's say, GeoGrid analysis. Also, you can actually have an understanding specifically where that load is applied. You can have an understanding by just clicking on the slice information, and you can switch to that specific slice and you'll see this load is applied, but that is specific reinforcements. But behind that is only one GeoGrid is applied here, and above that you see nothing is going to be calculated. So that's the only thing you need to consider into your GeoGrid and the reinforcements force option in this result view. Just want to go through the other questions on the chat box. Feel free to put your question in the chat box. I can still get back to you even after the time. We have still 4 minutes to cover the question, but I'll do my best to get back to you if you have any further question. Okay, so someone says, how can I see those GeoGrid library in my GeoStudio? You can simply come under the definition. You see all the GeoGrid libraries available under the definition. So if you click on the reinforcements option, currently I only assign the McCaffrey and Parlink. If you add a new one, if you want to see which GeoGrids library is available in GeoStudio, you can actually select the reinforcements type, because this definition view is not only for geosynthetic or GeoGrid, but also for anchor, nail, pile, and the user defined. So the GeoGrid libraries that we have is the last 4 option. Hoskar, McCaffrey, Tenkate, and Tensor are the current one which are available. If you select on the McCaffrey, you can select from the model here. The one that I selected was Paralink GeoGrid, and from this you can simply select all the types that are available from this drop-down menu. So the one that I selected for this example was Paralink 300. So you can actually select a similar one, and by just changing the input parameter, you will see these calculated factors are going to be changed. Specifically, when you want to see the reduction factor, you can play with the p-hash, or let's say the design life of your project. If you're designing for 120 years, or just basically is a temporary construction, you just design it for 2 years, or you can actually consider temperature into your design. So these are the things. Also, the other thing I mentioned during the session is the phase anchorage. If you consider the phase anchorage as true, it means that the geosynthetic is phased to the retaining wall. So anchorage to the retaining wall. So you can actually toggle this on or off, and you see it in action available here. All these factors are considered by our provider. So it means that the McCaffrey provide us a library of these, and it's already double checked with the McCaffrey. So if you think you need some specific library added into this one, and we don't have it, for example, available here, just feel free to contact us, and we can incorporate those libraries in under this GeoStudio library. For example, for Tenkate, the same thing. You need to select that, and you can select from the drop-down menu what type of Tenkate you're going to use as a GeoGrid library. I hope that I answered that question specifically. I'm going to read the other one. Kyle, I'm getting cautious of time. how much more time we have for today's webinar?
Oh, hi. Yeah, just you can continue answer another 2 more questions. I think we can just overtime a little
cool.
bit. Yeah.
Yeah. For those of you who don't have time to stick into this call, feel free to watch the recording because we just right on time at 5 p.m. But it's my time in Brisbane. But yeah, if you feel free, if you still have time to just stick to this call, I'm more than happy to answer the question. So the rainfall, yeah, that's a good question. Check the stability due to rainfall. Yeah, we do have the option to include it, but you need to actually couple seep and slope together. So you actually need to couple seep W analysis and slope W analysis if you want to consider the rainfall effect. So you can actually consider the boundary condition as an infiltration and incorporate the rainfall effect into your slope W by just updating. So actually CW dealing with updating the piezometric surfaces. So you can actually add the, let's say, infiltration versus time. So you can actually give a specific rainfall capacity, or let's rainfall intensity, and then you can see what happened within 2 hours rainfall event or 3 hours rainfall event. So you can do it for the worst case scenario and the best case scenario. So your piezometric surfaces is going to be updated, and you can incorporate the only the last analysis time, because you can run it CW as a transient analysis or a steady state analysis. So you can actually only use the last analysis time, or you can actually include all the time step and calculating the slope stability and the factor of safety basically for each time step of the rainfall. For example, after 1 hour rainfall, after 2 hours rainfall, what will be the effect specifically into your slope stability. This will be typically applicable for those of you who are dealing with a temporary construction, which rainfall is going to be affecting your result. So, so it reduces the suction strength by just saturating that area, so you won't have any suction strength, and it will substantially affect your slope W if you consider the suction strength into your temporary construction stage, because we typically suggest not to incorporate suction in a, let's say, long-term stability analysis, because when you have a heavy rainfall, you might lose it. So it's better to consider as the worst case scenario in the long-term stability. But since you're talking about the temporary analysis, so you can actually incorporate rainfall and the effect of a destructive effect into your slope stability analysis by just reducing the suction strength. Some of you asking us about sending the files. So we have the files available on our website. You can actually find it on our website. You just search McCaffrey GeoGrid library, and you can actually find this example with a PDF guide. Also, I gave it to Kyle. He will definitely share it after this presentation. In addition to that one, we have the engineering book for a slope W. So if anyone have any doubt about the theory and background behind the solver, so you can actually refer to that engineering books and have a look and get back to us if you have any questions specifically about the engineering books.
Okay, Zane, I'm afraid we have to stop here for the Q&A part.
Sure.
Yeah, we need to wrap up.
Yeah, I will answer the rest of them because I keep seeing them populated in the screen. So I will answer them after this webinar, but I give it over to you, Carl, to finish up and wrap up.
Yeah,
thanks everyone for joining today's.
Thank you so much for the Q&A. That will and also we appreciate everyone, especially those asking questions. I can see you have lots of passion on this, knowing the GeoStudio and also supporting our webinars. Unfortunately, we don't have enough time. We're already out of time, so we definitely will back to you after the session. Answer question one by one. Yep. So there's one thing I want to mention before we wrap up is we have local people who help you on the GeoStudio software. So we have Jamie Hao in Southeast Asia, and Sindaha and Amal in India, South Asia, and me in Australia, New Zealand. So feel free to contact us. Of course, we will back to you after webinar about the all the recorded videos and the question you asked during the session. Yep. Well, good. Thank you so much. Have a nice day. Thank you. Bye-bye.